try to share everything, and that usually works best on these deals. Okay, can we see the slides?
Uh,
Is it good? Can you see it?
yes, ma'am.
Yes.
All right,
Yes.
awesome. And so today we're going to talk about one of those kind of bugaboos that's always about in ham radio, SWR, and find out if you should care about it. And some people do more than is healthy, in my opinion. So what is SWR? We all kind of know what it is, but it's certainly not a breakfast cereal or a floor polish either. And it's not a way on CW to say slower. But it can indeed be an obsessive compulsive disorder, and you may know somebody like this. But we all know it as standing wave ratio. Some people put a V in front of it, as in voltage standing wave ratio, but it doesn't matter to me. When we're talking about wave mechanics, it's just standing wave ratio. So we'll do a little bit more about that in a minute, but you can see some examples of what this might be and what we're going to talk about right here in this little picture. Now, we all know that guy, right? And I know one personally. 1.12 to 1 is just awful, and the entire station has to be rethought. Other people will say that resonance is a 1-to-1 SWR. This is not necessarily true, although it could be. We also hear people say all the time that power is wasted when you don't have a 1-to-1 match. Well, that's not entirely true either. Some power might be wasted, but it's better to understand exactly what's going on. And of course, you get people all the time that say, well, I just feel better when it's 1-to-1. And at that point, you're bordering on some kind of, religious adherence to the 1-to-1 SWR ratio, because it's not what the science will tell us. So if you've seen my talk, Ground is a Myth, which some of you might have, it's not like that exactly. Ground is indeed a myth, just to whet your appetite for something like that. But there are many misconceptions about SWR. There's definitely a clear mathematical definition of what SWR is, and it does have value to us. We can use it profitably to figure out certain things, but not everything. So it's not a myth. But let's dig deeper. In order to understand SWR, we have to understand some basic wave mechanics. And we're going to try and do this in a way that's not electrical to begin with. So we'll use that to see what SWR is, how we might calculate it, figure out what we're actually measuring, and then figure out from that what we should care about. So we'll start with wave mechanics and study wave propagation. And of course, to begin that study, we have to define what a wave is. So a wave is kind of any disturbance in any kind of a field, and field is a mathematical construct. But think of it as some medium. Often these things are oscillating, which means they're sinusoidal. They don't have to be, but in some cases we're going to talk about it. In other cases, we're not going to talk about it that way. And these waves can be in different media, the electrical ones, so the ones that hams care about, but it can be mechanical, which we're going to dig into a little bit. And of course, quantum field theory is all based on wave mechanics because of the harmonic things that come out of the equations. And we've recently discovered that gravity seems to behave in a wave-like manner. So that's all pretty interesting. So wave motion in the oscillatory case. I'm sorry? Are we good? Okay. So in the oscillatory case, it's simple harmonic motion. You may have studied this in high school physics. And so the governing equations are the simple ones that we've come to know and love. A is the amplitude, sine omega t, that's some frequency. 2 pi f is what omega is, the radian frequency. And phi is some phase that is shifted by. And the wavelength, we know that. That's the velocity over the frequency. And then if you're an electrical engineer, you can do it all in complex arithmetic and e to the j omega t or some variant thereof. And we use j in electrical engineering not to confuse square root of -1 with current, which is a problem. So mechanical waves, I think we'll start there because this makes it easier to understand because you can see it. You know, the electrical stuff is a lot harder to see, but you can also try this stuff at home if you have a rope or a piece of string. If it's the right flexibility, you might be able to just try this in your garage. It has reasonable speeds. You can actually see the waves propagating, and you can really, it's really fun to watch these things. And this picture is what's called a shive wave machine. There was a huge one at MIT in the biggest lecture hall there, and I never saw anybody use it, sadly, but it covered like I don't know, a third of the ceiling. It was pretty cool looking, and I heard tell you can buy these things for about $300. So one of these days I might pick one up. But they're really fun. I'll show you a little video of this thing in operation in a moment. So let's talk about traveling waves. Now you can see, hopefully you can see the animation. It's not very fast, so you should be able to see it. You can see that these waves that you're looking at appear to be traveling from left to right. And that we call them traveling waves because they travel that way. They move from left to right or something to something. And all the points are changing as they go. And the peaks keep moving down the medium. As you can see right here, that little red dot shows kind of one stationary point and things, the wave moving around that. And so this is what happens when you have an impedance match. We'll discuss what that means in a couple of minutes also. And in fact, in mechanical systems, there is impedance and there is impedance matching, and we'll see that. So first, I want you to get that notion in your head of traveling waves. And now we have to talk about superposed waves. So in a linear system, and that's a mathematical definition, it means you can kind of multiply or add two things, either outside a function or inside a function, they still work correctly. All the waves are independent. They're overlaid on one another. And I'll show you in an animation what this looks like. You see these two bumps. They go across each other, but they don't interfere with one another. So they seem to pass through and retain their identity. That's a characteristic of a linear system. So if we have multiple sources of some kind of perturbation in a medium like this, and then the things that are perturbed and cause something to happen, they'll just pass through each other like ghosts in the night. You can also see addition and subtraction below, where you see one stationary wave and one traveling wave. And if you add those two together, as you would in a linear system, you can do that. You get this thing below that seems like it's not moving. It seems to be just going up and down in one place. But in fact, everything is moving. So superposition is a really important principle in these kinds of systems. And of course, they're not perfectly linear, but they're linear enough. Boundary conditions are one of those concepts that don't get talked about enough, in my opinion, when we're talking about things like standing wave ratios or even electromagnetics in many cases. Boundary conditions are what happens when you get to the edge of some medium. You know, the things change right there. So if we have, in these diagrams, we have horizontally, that's like a piece of rope. Think of it that way, or a piece of string, but rope's better to think about. And on the right-hand side, the vertical line is a wall. And the question we're going to explore here is that rope end by the wall free to move, or is it fixed in one position? And so we're going to flick that rope and then see what happens. So if I flick the rope and it's free to move like that, you can see that what happens is it gets to the end and things have to match, like it can't suddenly change out of the blue. And what happens is that there's momentum there, and all that momentum has to go somewhere. And so it actually ends up reversing direction. You can show this mathematically. I'm not going to bother with that right now, but you can see that the momentum goes down, it goes to the wall, and it has to match, so it goes back. Now, the next one is where it's fixed. And it's a little harder to see why it does what it does, but it has to do with conservation of momentum. So the wave goes down and it actually flips over when it gets to the end. And this has to do with making sure that the momentum stays the same instead of the position, and all the forces match up. So if we have an open thing like this, and you can think of it like an open piece of coax, for example, things come back with the same polarity that they arrived with. And if we have something that's fixed, and you can think of that as like shorted, then things flip over. Now, there are many intermediate conditions. This is just the extreme side. So let's look at an intermediate case. So if we have different boundary conditions where in the middle we go, for example, from something kind of more flexible and thin to something more thick and harder to move, you can see that it's sort of like being fixed against the wall. So we get this partial condition where some of it moves forward in the same polarity that we had, and the other part it's like harder to move, so it flips over and comes back. And then the reverse situation, you see it move forward, like we saw before with the where things were not fixed against the wall. And in all cases, the rope has to remain continuous. It has to, all the points have to stay. Nothing can jump around. Let's put it that way. So in this situation, energy and momentum are conserved. And then sometimes we get a reflection one way, and sometimes we get a reflection the other way. And that depends on, in the case of these mechanical waves, the kind of stiffness of a piece of rope or string. Now, how do we get those standing waves I talked about before? Well, they kind of they happen when we have some kind of a mismatch, and I'll describe a mismatch in more detail later. And they're not really stationary. They're just kind of the peaks and the troughs of the addition and subtraction of waves. And once again, superposition is working for us here. So we've got two waves in this case, traveling in opposite directions, and we add them together, and we get this seeming stationary pattern. And the pattern is indeed stationary, but the actual waves are not stationary. So you have to kind of get these two notions of things that are dynamic and things that appears to be static, but really aren't. And if we look at the peaks and the troughs here, we get an idea of where we're heading with this standing wave ratio idea. So here's the standing wave ratio, and mathematically, and that's the ratio of the peak to the trough of the envelope of these signals. So before you saw a bunch of sine waves moving up and down, but if we look the entire envelope, we're going to look at the peak of the envelope versus the trough of the envelope and get that ratio. And this very same calculation applies to mechanical waves. We just have to figure out what the impedance means and the reflection coefficient and all that stuff in that medium. It'll be something like deflection versus force or something like that. We can come up with a couple of different ways to define that impedance. And in the case of our electrical systems, we have the differences. Basically, it's all about the difference between the electric and magnetic fields. And that's how we ultimately end up defining impedance. But it does have a rigorous definition. And at the bottom, you can see that the standing wave ratio is computed out of this thing called the reflection coefficient. We use the Greek letter gamma to define that. And we take the magnitude of that because that can be complex. If you remember from your extra test, impedance is expressed as a complex number, and gamma ends up being a complex calculation. And then you can strip all of that off and just get the magnitude to get the standing wave ratio because it's a real value. Now I want to show you a little animation here that I stole from the internet that describes characteristic impedance. So it's the ratio of a couple of parameters. It's the deflection or tension in a rope. It's kind of constant for a constant medium. And it's determined all by the physical characteristics in the medium. And for electrical systems, you can see you can model it with a capacitor and an inductor. And this animation I'm going to start in a second here will give you a bit of an idea. We're going to pump some energy into the system, and you're going to see it propagate, first into the magnetic field and the inductors, and then the electric field and the capacitors, and it's going to move down in sort of daisy chain fashion down this thing. And I want you to watch carefully what happens when it gets to the end. So I'm going to set it in motion. And you can see it start. And the lifting is kind of like voltage. And then you can see those current arrows as it moves down bit by bit. And you can see the energy is just being coupled from chunk to chunk to chunk to chunk very cleanly. But when it gets to the end, you'll see what happens. So the energy is moving down this thing, and then it gets to the end and it has nowhere to go. And so what's it going to do to, keep those boundary conditions? It's going to have to start moving back because it's got nowhere else to go. And this represents a mismatch. But the point at this slide I want you to notice is that there is a characteristic impedance where the energy will move, bit by little chunky bit down some medium, which might be, for example, a transmission line or a piece of rope. So now let's talk about what a match is. So we have this medium and we have stuff moving down the medium. And when we have a match, all of the energy that's in a particular segment of that medium gets transferred to the next segment without any problem whatsoever. It just gets transferred or, for example, absorbed down this thing. And we're going to see the Shive wave machine in motion here to demonstrate that. Work that's done from one segment to the next is force times distance in a physical system. There's other definitions in electrical systems. Worry about this in a mechanical system for now. And because of the work energy theorem, work is the same as energy. And that means that every chunk, every packet of energy, if you will, that's in one segment of the medium will get transferred to the next segment cleanly without anything left over. So let me show you this. So the guy puts a little energy into the system and 2 deflections. And what you'll see is that it gets to the end and it's all perfectly coupled and it disappears. And why does it disappear like that? Well, there's actually a dash pot on there to absorb that energy and turn it into heat. And so it gets to the end and the energy is transferred into heat. And so it doesn't start back the other way. If we have a perfect match, energy is always transferred and we get this unidirectional propagation. It just keeps going and it doesn't come back. Now, at this point, you're probably saying, well, this isn't ham radio. What the heck are we talking about with pieces of rope and, Shive wave machines and all that stuff? But actually it is. And you can think of deflection in a rope as voltage, or at least that's the way I like to think of it. Or the tension in the rope might be current, or the force and tension are sort of equivalent. And they have similar constraints. We have changes in thickness. We have shorted as like something held stationary, open is something that can move around. And this is sort of an analogy, it's more than an analogy. It actually has physical significance that transfers between the two. The governing equations are the same. And in a piece of coax, we have those very same kind of waves. There's a medium which happens to be space-time, where we notice that electric and magnetic fields propagate and radiate. And it's very similar to a rope, except for now we have twice as many things to worry about because we have 2 kinds of fields. And those 2 kinds of fields are coupled to one another. So they propagate, though, down in a very similar fashion. And they have a characteristic impedance, which is how it can move little packets of energy. So every time you have an electric and a magnetic field, that represents potential energy in there. And we move it down this quote unquote rope that's actually a piece of coax. Open feed line is maybe an easier way to think about this or even demonstrate it to yourself. We have 2 conductors out in the open instead of this enclosed thing where you can't see anything. And it has a different characteristic impedance than we're used to. But you can put a light bulb or an LED or something like that and a loop of wire out there, and you can actually measure those fields. And since the fields are external, that's why open feed line, you have to be a little more careful about where you put it. But you can actually see, for example, standing waves. So if you have a bit of a standing wave ratio there, because you have a mismatch, you'll see the light change brightness as you move it down the piece of feed line. I want to take a moment here and talk about the Smith chart, which a lot of people are really scared of. But I think it's cool, and I want to use it to illustrate a concept that I think is really important. It's a really great way of estimating impedance. You can work with SWR, and that's the thing I want to focus on a little bit here. And believe it or not, since everything is linear, this thing is system impedance independent. You know, we like to think of our all systems as 50 ohms, but they're not. You know, a cable TV, for example, in the US is 75 ohms. We have 300 ohm systems, lots of different impedances. So it doesn't have to be 50, but at the center of this chart is a 1.0, and that's something where we normalize all those impedances to whatever we want. And this, for you mathematicians in the audience, this is actually a conformal map, which means all the angles are preserved of the gamma, the reflection coefficient, with a bunch of other stuff laid on top of it. So let's talk a bit about the construction of this chart. There's this thing in the middle called the prime center. That's where you see the 1.0, and that's where you scale everything. So if you want to have 50 ohms be your scaling, you multiply everything you see on here by 50. And so you make the center be 50. It has resistance circles, which you can see here, the blue example at the top, and you can see just the resistance circles. They center on the right-hand side, and then you can see different resistances, and those are all scalable resistances, so you multiply them by whatever your system impedance is. And we'll see later that we have SWR circles. Those are really the key point I want to get to. And rotation, usually in the counterclockwise direction, is distance. So as we move down, for example, a piece of coax, we're going to rotate a point around the prime center there. And again, all of this is normalized. And you can see also that it's on the complex plane. So we have the real axis is the horizontal one, and the imaginary axis is the vertical one. And on the bottom, you can see that we have reactant stuff as well. So we have reactance, resistance. We overlay the two on top of one another, and we get this more interesting looking thing on the bottom right, where we have intersection points. And with the resistance and reactance, we can pick out any complex impedance we want just by finding where they intersect. So you can see, for example, in the top, the bottom right diagram, again, you can see 0.5 plus J1, and that would represent an impedance of, let's say, if we had 50 ohms in the center there, so that would be 25 ohms plus J50. So that would be the complex impedance at that point if we normalized it to 50 ohms. And then we put the SWR circles on top of that, and now it's almost unreadable. And this is why you look at that thing and you go, boy, this is crazy. But this is actually helps us figure out some stuff. And the circles, you can see that they intersect the right-hand side there, and that's where you read the SWR off. And that doesn't get normalized. That's just a value because that ends up being a ratio. So you can see that circle with where they point to it intersects the right-hand side of the real axis at 2. So that represents an SWR of 2. The next circle out intersects at 5. So that represents a SWR of 5. And then the one on the outside is infinite. So with this interesting tool, how do we, I'm not going to quiz you on this later, so don't worry about it, but how do you find an SWR? Well, you might start with an impedance. And of course, you scale that to whatever your system impedance is. And you plot that point on the Smith chart. And then you make a circle centered right in the middle. And that is an SWR circle. So for that impedance, that's the SWR all the way around that circle. And those are all equivalent impedances as far as SWR is concerned. The radius of that in complex plane happens to be the reflection coefficient. That's not as interesting for most of us, but again, we want to find SWR, so that's where that circle intersects on the right-hand side of that real axis. So in this case, I don't know, something like around, I don't know, probably around 4 or something like that to 1 in this example. If you want to find impedances, you kind of work the whole thing backwards. You start with your SWR on the right-hand side of that real axis, and then you draw a circle centered in the middle, and you make that circle around again. You have that all the impedances along that circle are the same SWR, and those are all equivalent impedances, and the reflection coefficient is the radius again. But notice all the points on the circle are the same SWR. One SWR has an infinite number of equivalent impedances. It doesn't matter. But who cares? Well, the thing that this has shown us is that SWR is what I call a degenerate metric. It tells us some things, but it doesn't tell us everything by any stretch. There's a whole bunch of duplicate information put into the standing wave ratio. In fact, there's an infinite set of impedances that map to the same SWR. And the absolute impedance doesn't matter. No matter what impedance you start with, you'll end up with an infinite number of equivalent impedances that give you the same SWR. And so SWR it's really, to be really clear, it just tells you something. It certainly doesn't tell you everything. So what we learned from all of this, the absolute load doesn't matter. Resistance is resistance. It doesn't matter what the medium is. We can calculate resistance the same way. The wave mechanics are the same as no matter what the medium is. Things don't change. Energy propagates. It propagates in some fashion or another through propagating fields, might be through a mechanical medium, and it might turn into heat. But of course, energy is conserved, so it's got to go somewhere, and we just have to find out where it goes. Now, to get energy into a system with these waves, before we were flicking a piece of rope with our hand, we might call that the generator. That's the thing that puts the energy into the system to make the waves that propagate through a medium. And I want to talk about it more in ham radio terms. This is a picture of a FT100 that I rescued off of eBay and brought back to life. Now, there's a lot of confusion about these things called generators. We call them transmitters in ham radio. And what the equivalent circuit of a generator or transmitter looks like, I think there's a lot of confusion. These things are designed for a particular system impedance, whether tubes or transistors, it doesn't matter. They don't have to operate there, but they like to operate there because that's what the engineer who designed them for. And the question we'll have to ask about this generator or transmitter is, can it deliver power? And can it deliver it efficiently or without breaking? I'll take a minute here to talk about one of my pet peeves in electrical engineering around this topic, and that's called the maximum power transfer theorem, and it is so often misapplied. It drives me nuts, to be honest. So the maximum power transfer theorem vaguely states, and I'm going to leave out how this gets abused, that the load impedance and the source impedance have to be the same for a maximum power transfer. And that's true with a particular assumption in place. So the abuse that happens in many of these explanations is that the source impedance must be a fixed value for this to be true. So if I allow myself to change the source impedance, then this no longer applies. So and the source and load, both variable, I can pick anything I want, and then things don't work the way that you think they are. So if you have a source and you say, well, a voltage source like in that schematic, and you say the source impedance is fixed as 50 ohms, and I say, okay, well, I can't do anything about that, then I have to make the load impedance 50 ohms in order to get the maximum power. But if you allow me to change that R sub S, all bets are off. So let me show you how that works. And I like to illustrate things with degenerate cases. And so for let's say we fix it at 50 ohms. Let's calculate the power. So if we can change the source, and I'll say that the source voltage is 50 volts. I'll make the source 50 ohms, and then we'll make the load 50 ohms, and we'll do the V squared over R calculation, and it comes out to 12.5 watts. Okay, cool. But now, since I can change the source resistance, I'm going to change it to 0. Why not? And if I change it to 0 and we do the same calculation, V squared over R, it's actually simpler now. 50 squared over 50, it's 50 watts. I can deliver 50 watts to that load. So you can see that just having them the same is not actually what this is all about. It only applies when the source resistance is out of my control. So what's the source impedance on a transmitter? Well, if you look at the schematic of any transmitter, you won't find a 50 ohm resistor in there to be that source resistance. It's something much more complicated than that. It's not, seems to be this funny notion that there's a 50 ohm resistor in there somewhere. It isn't. The transmitter looks more like a voltage source being driven, at some frequency sinusoidally with some variations. And it kind of looks like something that just wants to match to 50 ohms. The actual source impedance is complicated, changes throughout each individual cycle, but you can think of it more like a voltage source that's happy to deliver power into a 50 ohm load by design. Not that it has to see 50 ohms, it's just known to be happy at 50 ohms. So what the transmitter really wants, tube or transistor, doesn't matter. It wants a desirable impedance. It wants the design impedance. We want to keep the tubes or transistors really happy, because if we make them deal with too much power or too much voltage, and certainly in the case of transistors, they will just melt down. In tubes, you might get an overheating plate, or you might get an arc. We also want to keep these things in their linear region so that they act in a way that's doesn't cause all kinds of harmonic distortion and other problems. So we want to keep them linear. We want to keep them efficient. And in our case, it's often 50 ohms. And older tube transmitters, they weren't designed for 50 ohms at all. They were designed for you to match them into some band of loads that you might have. So they contain a matching network built in. Now, of course, the transmitter is an imperfect device, and it kind of wants 50 ohms. It's happy there in most of our cases that we care about. Transmission lines are also not perfect. They try to get energy from point A to point B, but they also have resistive loss. They have this thing called dielectric loss, which is these dipole molecules in the medium in between the conductors, kind of flipping back and forth and creating friction in the form of the fields yanking on the lattice of the molecules that make up the dielectric. And then there's leakage. Energy isn't perfectly contained within, say, a piece of coax. And what does SWR mean in this context? Well, it means that we're going to have sections of that coax where, instead of being kind of the same amount of voltage and current all along the coax, we're going to have places, kind of hotspots, if you will, of high voltage and other hotspots of high current. And this could mean more loss. It could mean in the form of heat. It could mean more leakage. It could mean that we actually get arcing in some place where we get ionization paths. Now, coax loss can be calculated to a reasonable estimation. In coax, it's a lot higher than open wire feed line because of the dielectric, and also the leakage loss tends to be higher. With open wire feed line, it's actually canceling, so as long as you keep it away from things, it tends to be pretty low loss. But for coax, it depends a lot on that dielectric material in the middle, and each coax type has its own dielectric material and dielectric thickness, and the dimensions matter. And then there's the braiding on the outside. The shield makes the loss different in each one. But there's a general calculation you can do to figure out what the loss will be. for different SWR values. So different ones where we have those hot spots of voltage and current. And it's the ARL matched loss calculation. You can see it here on the screen. And you can, what it means is you can take a piece of coax that has a known loss. So most coax has a published loss per foot, for example, at an SWR of 1 to 1. And that's just because of, resistive losses and other things. And so you can take that and you can scale it for a given SWR. And so you see you have that that row thing that looks like a small p. You take the SWR, you calculate that, and then you plug it into this thing and you can get the additional loss. And if you don't want to do this on your calculator, you can use the online calculators. There's a bunch of those, but I'm going to show you an example. So this I stole from the November 2006 QST, and it shows how to, like as an easy chart. So if you start on the bottom with the line loss in decibels per unit length, whatever it may be, and this will show you the additional loss, which is on the vertical axis, that's caused by having standing waves. And if you say you have an example on the left, I just sort of calculated from the chart. If you have 1 dB per unit length, whatever that may be, it doesn't matter actually. 1 dB per unit length, let's say it's a foot. That would be really lossy, but let's say 100 feet, okay? And then we have a 2 to 1 SWR. We're going to have an additional 0.2 decibels of loss. And you can add decibels because it's logs, and that gives you the increased amount of loss. 5 to 1 is 1 dB, and 10 to 1 is only 2.2 dB. So the thing to notice here is that the loss really isn't that huge. It's significant, but it's not amazingly bad. So, at 5 to 1 even, it's only 1 dB per say 100 feet. It's not that bad. It could be a lot worse.
Christian?
Yeah.
Can I have a question?
Mm-hmm.
So it seems like most people are either as concerned with A, protecting their transmitter, or
Mm-hmm.
B, getting the most signal out, right?
Mm-hmm.
And with a solid state transmitter, protecting the transmitter is probably number one, and that, so when we talk about the reason we're all worried about SWR is because we think it's going to damage our transmitter. The other question I had, which is kind of a side one, but you might touch on at some point, there's been a lot of discussion that I've seen online on various social media sites about the whole idea of reflections at both the source and the destination. In other words, when a wave gets reflected at the antenna, it comes back to the transmitter where there's a return load in effect, right? And so the question is, does the SWR kind of total or the power bounce back and forth, losing a little bit in each reflection, but still adding a little bit more to the antenna with each reflection? Does that even happen? There was a lot of people say, oh, it doesn't happen at all. Other people say it happens a lot. I'm not sure. What's your thought on those?
Okay, so the transmitters, modern solid state transmitters and amplifiers, are pretty well protected. I wouldn't say throw anything at it, but usually they will fold back and do the right thing in most cases. So I wouldn't, if it's more than, certainly 3 to 1 is a reasonable limit. Don't worry about anything 3 to 1 or anything below that. And when you get up in the 5 to 10 region, maybe you should probably turn the transmitter off and figure out what's going on. So that's that part that, you just want to keep that transmitter happy. As for the bouncing back and forth, sure, it happens to a degree. So some transmitters it depends on how the transmitter or the generator reacts to the energy coming back, because energy goes down to the end, is not perfectly matched. Those packets of energy travel back down the coax in the other direction. And then the transmitter will either reflect some of that back, depending upon its instantaneous impedance, or it may absorb some of it and warm up the finals more. and that factors into its power budget before it gets too hot. And so energy does bounce back and forth, but this is not, we don't have a Zeno's paradox going on here. It actually does settle to a value, and the loss will be reflected. And this loss, for example, this matched loss calculation has all of that built in. So you're not going to see extra loss because of that. But it does indeed go in both directions and bounce back a bit. But it does settle.
Yeah, so maybe that settle time is so quick that the sum of all of the losses, is it doesn't grow that much.
That's right. That's right. It settles almost instantaneously. Speed of light, kind of instantaneously.
Yeah. Interesting.
All right. And I may touch on some of these points again in a couple minutes. So we have this transmitter, we have a load, we have a piece of coax in between, and we have to make the transmitter happy. That's our goal here. What do we do? And so we use a matching network, and we have to figure out where to put that matching network. And it could be near the transmitter, which is certainly very convenient. And however, the trade-off there is that the feed line has to deal with this high SWR inside of it and the subsequent loss, which we just talked about. Or we could put it up near the load or the antenna, which is efficient, but it could be a pain because we have to protect that thing from the element. We have elements, we have to control it remotely. So that could be an issue or not, depending upon your setup. So then matching networks look like this or like other ones. We have to null out the reactance. We do that by creating a complex conjugate. So we try to get the complex part to go away. Since this is all linear, we can add them together. And so if we have, a capacitive one, we can add an inductive one to compensate. We can also, in the network, essentially transform the resistive part of the impedance to get it to be happier. Again, I hate to say, we're not tuning anything. We're just making the transmitter happy to get it to the feed point. Hopefully transfer as much power as we can out to the load. And the load is, being an antenna, is going to be both reactive and resistive. The resistive part's the one we care about. That's the radiation resistance. That's the equivalent resistance we want power to go into to get the fields to propagate away. But when we design this network, we kind of want to avoid network losses, and that requires choosing components that won't have losses. Like, for example, if your matching network has ferrites in it, ferrites can be pretty lossy, depending upon how much you saturate them, because they have little magnetic dipoles in them, and they vibrate back and forth and get hot, and that can cause significant loss. Also, dielectrics and capacitors. So what about the antenna? We've kind of given that short shrift so far, so let's talk about it a little bit. Most antennas are not 50 ohms. I think in my last talk I might have mentioned this. A free space dipole 72, free space monopoles 36. Yagis are super low impedance in the teens. So what do we do here? Well, this is where our matching network comes in. And most antennas, if you find that they're matching to 50 ohms, like a lot of times this happens with a monopole in the field. So you set up something with a loading coil in the center, like 4 radials or something. You say, wow, 50 ohms, awesome, let's go. Well, that's 50 ohms because it's lossy. You're heating the dirt to a large degree. And of course, when you have these different antennas and you start changing how they match, what the feed point impedance looks like, you'll be tweaking the pattern too. So you'll have to be aware of that. So in the end, what do we care about? We want to make the transmitter happy. That's the real thing. To make that happy, we use a matching network pretty often. That matching network has to be efficient if we want to have an efficient system. So that's something to care about. A lot of your, really compact tuners are not that efficient because of the magnetics and the capacitors that they use. We account for the loss in the feed line. I showed you the matched loss calculator. For a short run of coax, maybe no problem at all, even if you have a relatively high SWR. For a longer run, well, you might want to think about it. Could be an issue. So, just calculate it and see if that's something you can tolerate. If it's an HF set up on 160 meters, maybe who cares? If we're doing EME, well, that's a totally different story. We may want to care about that a lot more. So, other than that, we just want to get out there and have some fun on the radio and not stress about this too much. So if you want to learn more about this, the ARL handbook has a reasonable treatment of SWR. The antenna book has a bit more about this, although they don't dive into the theory that much. Wikipedia has some reasonable but terse and obtuse articles about SWR and wave mechanics. And of course, any physics text from usually second semester college physics will have this kind of stuff in it that can get you a deeper dive. But the handbook and the antenna book, I think, will serve you well. So with that, I will take some questions.
So one of the most popular antenna types today are the multiband antennas, where, like using an off-center fed or an end fed, and then you have this balun or this unen, I guess technically it is, in there, which causes the thing to quote resonate at different frequencies, which I don't fully understand that. Why you get those dips in just the right places. And I'm not sure how that relates. It does relate a little bit because a lot of times when they talk about antenna feeding and matching, it seems like the assumption is always that you have a resonant antenna or that you're only working on one frequency. Well, of course, none of us do that. We're all working on multiple frequencies, and many times within an antenna that is, can be used on multiple different bands, so wide frequency ranges. I don't think it really, I guess my question isn't really related too much to the theory that you just presented, because the theory is the same no matter what you're hooking it up to, right? But what are your thoughts about matching these type of antennas, these multiband, wide bandwidth antennas?
So let's talk about the notion of resonance first to try and untangle this. So just because something is 50 ohms doesn't mean it's quote unquote resonant. Resonance itself has to do with, does the wavelength match the length of the antenna, with the propagation of energy down to the end. The antenna is going to do something no matter what you drive it with. And moving the feed pointer around just changes the apparent impedance. It doesn't change resonance. The antenna is going to do what it's going to do. And you drive it, it's going to be closer to a point of resonance, of which there's only one, by the way, or not. And you're just going to force it into different electrical configurations. The idea behind the off-center fed antenna is that, there sort of be places where the impedance is happy for you and other places where it's not happy, is to move that around so that it's not unhappy. And by unhappy, I mean something that you could never match realistically, so that the unhappy places are not on the bands of interest. And so we changed it. This is the same thing as the G5RV. So the G5RV, we just pull it off in the center instead of off center. And then we have this transmission line transformer, which transforms the impedance to something else that you have a hope of matching with a matching network. So it's not that the antenna has multiple resonant points or anything like that. It just has places where the impedance is one you can deal with. Does that kind of answer it?
I think so. When you say that an antenna only has one resonant point, what happens when you, energize or excite an antenna at a multiple of its so-called resonant frequency, right? So if I have a wire antenna that's resonant at exactly 20 meters, and then I excite it with 40 meters or 10 meters, you get a different number of peaks on that same wire, but isn't that still a resonant point?
Those are various harmonic resonant points or subharmonic resonant points, or places where the wavelength kind of matches something interesting. But what you see is that it's just like a transmission line where you get these inversions every quarter wavelength of impedance. So if you think of a dipole, the ends of the dipole are free to move electrically, more or less. So they're open circuits. And
Right.
if you go down to 40 meters and you have an open circuit, now you have an eighth of a wavelength there, and on a 20-meter quote unquote resonant, where it's a quarter wavelength on each side. Well, start with 20 meters, okay? So we have a quarter wavelength piece of wire on either side, and so we get an impedance inversion. So if the impedance at the end of the dipole looks open-ish, then the impedance after that quarter wavelength is going to look short, sort of like shorted. It's not exactly shorted, but it's going to look like sort of lower impedance as opposed to a high one. So that's on both sides of the dipole. So if we go to, say, 10 meters on that, then we're going to get two of those flips. And so we're going to get a different impedance. If we go to 40 meters, we're going to get a half a flip. And so we're going to get a different impedance again. And what the net effect of this is going to be, other than the feed point impedance being a totally different thing than it was before, is that the pattern is going to change a lot. So the energy is going to go out there, and it's going to interact with the space-time, and the pattern's going to go crazy. And you see this if you look at the patterns for G5RVs. I think in my last talk, I may have even showed some of those patterns. Like the G5RV Junior is in a reasonably good configuration for 20 meters and gives you a nice sort of double toroidal pattern. But on other bands, it gets really spiky and weird. So that's what happens. You get different feed point impedances, sometimes really bad feed point impedances. And you might get, like if you get to a half wavelength, then that's a really bad impedance, because open starts to look like open at the feed point. So sometimes you will be able to match it and sometimes you won't. And then you'll get these variations in pattern as you go.
Does a high voltage on a wire or an antenna at a specific point, does that correspond to a place where radiation is leaving the wire? In other
That's
words,
more of a minimum radiation point.
Yeah,
Yeah. So what, because of the way that impedance works out in free space, current is where most of the good coupling occurs. So when you get a high voltage, that's usually not, it doesn't couple well at that point into space-time, into propagating waves. So the high current points are the points where you get the best coupling. So for example, if you have a loaded antenna, let's look at a loaded monopole on a car or on the dirt with radials, and where do you put that loading coil in the antenna? Well, it turns out that the best place to put it is as high as you can possibly get it without it having such high voltage that it arcs over. And what that does is it forces the high current portion to be on the bottom. The low current portion will be above the coil. And so that high current portion is where you get most of the coupling into space-time. So if you have an antenna, like I had this antenna, it was called a PAC-12. And I don't know if they're still made, but it's a little portable, very lightweight field antenna. And it had a very short, maybe, 18-inch segment to lift the coil off of the feed point that was on the dirt. And so what I did was I bought two more of those 18-inch segments, maybe three, and I pushed it way up, and the antenna performance improved dramatically just by getting the high current portion to have a larger area. So current is what you're after.
I see.
Hi.
Yeah.
Yeah, hi, Kristen. Thanks for the talk. Very interesting. I hope my audio is coming through. I've still got these broadband problems. So I mean, flippantly, the way I always deal with the people who say they're obsessed with one-to-one SWR is that I've got a very good dummy load that's 50 ohms and gives a great perfect SWR, but it doesn't radiate very well.
Exactly.
Um, I wanted to sort of put to you the scenario which some people I've seen come across where they think they've got a very good match. They think they've got the SWR meter tells them a good story. But actually, if they lengthen the coax at all to their load, then they find that it's not, and so actually they've got a problem because it's just lucky that the coax is a particular length in their case, and it's providing it's affecting the SWR measurement, and a lot of people get caught out by that, where they measure something and think that they're measuring something that's very good, but that doesn't necessarily mean the case, because you can have other factors like the imperfect coax, imperfect feeder, being a particular length that gives you a good reading.
Yes, exactly. And both of the points you made touch on the same thing. About the SWR circles on the Smith chart. So, that 50 ohm resistor lands on the Smith chart and says, okay, that's a perfect match. And so you just say, okay, well, that's something interesting. But again, SWR is a degenerate metric. And the same thing for the coax length. So when I see SWR should not change if you have a matched load.
No.
So you match it on the end, then there are no peaks and valleys. Everything matches, change the length, no problem. But when you see it changing like that, that means that the piece of coax is functioning as a transmission line transformer. And those peaks of current and peaks of voltage that I talked about earlier are along that coax. And as you change the length, you put yourself at a different place amongst those peaks.
Yeah.
And thus the apparent impedance changes. And once again, you're on a SWR circle. And so, sometimes you see an SWR, you're like moving around on that SWR circle and changing the radius.
Yeah. Yeah. Yeah, you can see all this on the analyzers we have nowadays, which you could never see before.
That's right. That's right. You can look at the complex impedance
on these VNAs. Yeah. Thank you.
Sure.
Anybody else have any questions?
You mentioned Zeno's proposition.
Oh yeah, Zeno's paradox.
Yeah, paradox. I learned about that a long time ago about a Johnny joke, and they was trying to be explain it to in a physics class, and Johnny's he's a rapscallion type of guy. And the teacher says, "Well, Johnny, what do you not understand?" He says, "Well, I don't understand Zeno's proposition." He says, "Well, look at it this way. Mary's up front and you're up back. And if you travel halfway to her, and then that forms a distance again, and then if you traveled half of that distance, and that forms another distance again, which is halfway to Mary again." And he says, "How close did you ever get to Mary?" And the teacher is looking for the answer of, "I can only get to halfway to Mary." And Johnny says, "Well, I could get close enough to do damage." And that's kind of how I look at some of the SWR stuff that we're talking about today, is that so many people have relied on thinking that a toroid is the panacea of all problems to make an antenna radiate. And in truth, I mean, a non-resonant wire radiates just fine, and it can just be fun. And people are going to all kinds of mysterious things to market crap on all these trade journals, QST, CQ, and any other place you go. They've marketed crap that is exactly that. It's 50%. No place do you ever see anything about efficiency of an antenna when you're buying the damn thing. The problem that people really need to be focused on is takeoff angle, because that is probably more important than anything else to us. Yeah. If you got a takeoff angle that's straight up in the air, it isn't going to happen. You're not going to be working DX. You're going to try to work the moon. But if you got a takeoff angle that's 8 degrees, that is an area that we really need to discuss, is takeoff angles of antennas and why it's important. And
yeah, well, takeoff angles and patterns,
yes,
that's the thing that always gets me with the G5RV. Oh, it's a great antenna. I worked lots of DX, but that's all anecdotal. But every time you change bands on that G5RV, you've got a totally different scenario going.
Well, one of the discussions here said an off-center fed dipole. And there's all kinds of stuff written on them. Well, I put one up because I was playing with it, and we were in a WPX contest, and an off-center fed dipole at certain frequencies looks like a porcupine with a bad hair day.
Yep.
A bad hair day.
So does a G5RV.
Yes, exactly. It's the same damn thing. And so we're trying to work China, and we've got an array, a vertical array, and we can't get him to come back. And I says, Morgan, try this. He says, Dad, you don't know anything about it. I says, Dad, I do too. It could happen. And the first time he called him, China came right back. It was like, he said something foul to me about something to do to myself. And then he kept on rolling. But anyway, that's but one of the things that you mentioned was quarter wave transmission line transformers. And they're probably more efficient than any toroid that you could ever put together, ever, because of the hysteric losses in the toroid causing heat up and just totally energy loss by heat. So there's an antenna that demonstrates this really well, and that's called a in-fed folded dipole with a quarter wave matching transformer, and that's called a Slim Jim. And
that's very frequency specific, though.
That antenna has about an 8 to 10 degree takeoff angle, and it beats 8 VHF antennas in being able to hit a repeater 30 miles away that cost $100. You can make it for about $4 just because of the takeoff angle.
We once made an 80-meter Slim Jim and raised it into the air with kites.
Oh my goodness.
It was incredible. It was really incredible. It was slow and low noise as well.
Oh yeah,
straight up, right? And we were working all sorts of stuff on this. And when we told people we were using an 80-meter Slim Jim, I don't think they believed us, but it was a one-off.
That's hilarious.
Hey, Christine.
Very good.
Mm-hmm.
I have a question for you, a little bit around this. It is a propagation. Is it active or is it passive? With 1 watt, you can get the whole world. But how can you get that strong, small signal around the world when you can? There's no way you can deliver it. So sometimes I think that propagation must be active, not passive. What do you think about this?
Yeah, it's an interesting question. In order for it to be active, there has to be energy input from something that is at that frequency.
Yes.
Or it could also, rather than active, you could call it active depending upon your definition of active. There are very efficient propagation paths that appear from time to time. And they look like a transmission line more than just, an ionic fog. And so you can get extraordinarily efficient propagation. And that could be what seems like active propagation. You just get super favorable.
That's what I think. And also, I like sometimes to transmit direct up to not to the moon, but I like to be on 80 meter and go back to my own island. I like to make the skip inside like 500 kilometers, not going more far away. And then I like to make my wave straight up. And so there are scenarios where on, like example, on 80 meter, I like to transmit straight up. But I did have a question there, and somehow and somehow not. I'm speaking to my computer. It is AI. I call her Stina. She even made her own call sign. I thought that quite funny. And that is Gemini. And she is telling me every day something new. Like example, in old times, they find out that 77 ohm is the sweet spot for receiving, and 30 ohm is a sweet spot for transmitting. So that is why they made 50 ohm, to make it something there between. Have you heard about that story?
I haven't heard that particular story. My understanding is that it was a sweet spot for the mechanics of the coax, and that was most of it, the coax more than anything else.
It was in the Navy in the old time when they were trying to figure out what they should use. And then, I asked my AI, why do we use 50 ohm? And then the answer was the sweet spot for receiving is 77 ohm, and that is why television use 75. And for transmitting, you use 50. For the sweet spot is 30. And I thought it quite interesting. I never heard about it before.
Yeah, I'll have to research that. I hadn't heard that. But maybe it's true. Who knows? You can't
the
trust these
question
AI
is
things.
again, why are we using 50 ohm? And then that was the answer. It was something there between. But
Interesting.
I lost you in the time there, especially with the card, with the Swift card. I never understand it. It is a magic box, that card. But my standing wave meter have it. I know where the standing wave should be in a dot, but you can keep it for you at the moment.
Okay, it's once you get to know it, it's a really useful tool.
Yeah, the Smith card, yes. Okay, so thank you very much for this.
Sure.
Anybody else?
I think Morgan had a good point about and Kristen about the efficiency of the antenna. You did say about using matching networks and things in alluding to ATUs and or AMUs to provide a better match, and I wonder about how some people think that because they use the tuner or the matching circuit as properly called, to make the transmitter happy, as you said several times, it's not actually terribly efficient at that end of things either. Never mind the antenna efficiency. So, if a lot of heat is going out in the coils or the capacitor plates in your tuner, then it may look like a happy transmitter, but you're not getting it out very far.
Yeah, most definitely. And as far as those matching networks goes, if you want the most efficient one, you want those open air capacitors and open air inductors.
Thanks. Thank you again for the talk. Very interesting.
Sure.
Alan, you got that? You'll explain that to me later. Kristen, I can't thank you enough. Another excellent presentation. And
Well, it's my pleasure.
Anybody else have any last questions before we let her go? I think we got it. Thank you again. It was just superb.
I'm glad you liked it.
Thank you very much, Kristen.
Thank you. Take care,
Thanks.
everybody.
Bye.
Bye-bye.
We'll go back to our normal programming.
Right, I'm going to disappear because this broadband connection, I've done well to get it to last as long as the presentation.
All right.
So,
Take care, Jonathan.
Hopefully I'll be back on a better internet link next time. Bye.
Anybody else have any comments? Okay. Bye, Larry.
Take care, you all. It's been very interesting. Thank you.
Thank you for coming.
I'm going to fade out.
Dave, you got it all?
I do believe I did.
Okay, perfect.
So I was always under apparently now the misimpression that the better the SWR, the more efficient your antenna would be. But how do you tell if your antenna is resonant other than measuring it and put it in the formula to get the right length for the frequency that you're on? Is there any and is that always 100% accurate? So, if you're on 14250 and the antenna length is, I'm just going to say 60 feet for a dipole, is that is that 60 feet always going to be resonant for that frequency? Or are there other factors involved? I should have asked her that.
Well, one thing she did say it was that there's only one resonant frequency per antenna, period. So anytime you're not on that frequency, you're using the antenna in a less than resonant position.
Yeah, that makes sense.
So I think we use the word resonance, too often to think of it as like the one thing to work on. But, and then the SWR, the way I take that is that, and that was kind of my question, it's more about protecting your amp or, your transmitter than anything else, right? Because if your transmitter could tolerate an infinite SWR, none of us would care about SWR.
Well,
I
think we've been conditioned also.
Yeah, we really have.
Go buy this $600 meter to measure something that apparently you don't need to worry about.
I do think that you could generally say that if you have a good match to your antenna and transmitter, that you will be more efficient than if you had a really bad match, right? Because you're going to have less heat. I like the way she put it. The reflection, most of the reflected energy in a poor SWR is absorbed as heat in the output, in the finals of your transmitter.
Right.
That's why the tubes overheat. That's why the transistors overheat and blow up. It's because it's trying to absorb the heat from that reflected energy. So, if your transmitter could tolerate all of that heat and without blowing up, which we know they can't, but if it could, then we wouldn't be as worried about it, right? And then your antenna would be radiating as best that it can, and you'd be getting out. But we can't do that because we have to worry about our amps.
If I put up a whip antenna, the vertical antenna, that's 17 feet, and that's allegedly resonant somewhere in the 20 meter band, and I don't have any radials on it, I get an SWR. I'm going by what I did on the 2 days ago. I was using a Poda Performer, and before I put the radials out, I measured the SWR, and it was about 4.8 to 1 all across the whole band. I put one radial out, and it was 2 to 1. I put another radial out, and it was basically 1 to 1 across the whole band. But I never changed the length of that antenna. So is that antenna just as efficient without those radials at a high SWR as it is, or do the radials do they perform some other function aside from making the SWR good?
I think the way to think about the answer to that is that not to think of it as the antenna, but to think of it as a system.
Yeah. Okay.
The coax and the antenna together are a system. And when you have a poor match at, say, 4 to 1, then you're dissipating a lot of the energy from your transmitter as heat in the system, right? And therefore, you're not pushing as much out of the antenna. If you have a good match, 1 to 1, then most, if not all, the energy is going to be injected into the antenna. Now, that doesn't mean the antenna is efficient, right? All it means is that you're putting all the energy you can into it.
Right, that makes sense.
So the efficiency is a combination of the whole system, not just the antenna.
And I guess you could test that in real world by making a contact with, say, 2 radials and then putting 2 more radials out and making that same contact and see what they think about the difference in the
that would be a really interesting experiment, Dave. And a good way to do that would be to use either FT8 or just, you ever play with the whisper mode?
Yes.
I've just started looking at that, and I haven't really done it. But with whisper, you don't even have to make a contact, and it'll show you how you were received and what the signal to noise ratio was at various places around the world. So then you could try it with one radial, and see what kind of results you get using Whisper, and then put no radials in or two and see how they change. That would be a great way of testing that.
Well, I've done a couple other, and I always preface my results with the fact that it's not scientific. It's just, people telling me by ear. But there was one,
Yeah.
like one time I went out and I do these on a POTA thing, and I'll put the 17-foot telescopic whip in a mag mount on the roof of my car and a 20-meter mag mount on the top of the car on a 20-meter, ham stick, and an A/B switch inside the car. So how's this sound? Okay, how's this sound? Well, it's not as good as the other one. So, that's kind of like, you can have all the meters and numbers and everything you want, but I think the real world, yeah, I can hear that better than the other one is probably
Right.
But who's to say if I turn my car around to face the other way that it wouldn't be the other way? I mean, there's just way too many factors.
Which is why we go over and over and over and over it.
Yeah.
Yeah, I mean,